All right, so the last one that I want to do here has got some interesting peculiarities to it of a nature that we're going to have to contend with occasionally. So the first thing I notice is that this doesn't go n equals 1 to infinity, it goes n equals 0 to infinity. So we might need to sort of reconstrue this. You can do lots of different things. Like you can pull out one term and then make it n equals 1 to infinity. Another thing you could do is just sort of renumber it. So, we like to have n equals 1 to infinity so that all our summation comparisons have sort of a common ground. But there are lots of ways we can play around with this. So one thing we could do is say this is n equals 1 to infinity of 5 to the n minus 1 over 6 to the n. So all I've done is rename. When n equals 0, I have 6 to the 1. N equals 1, I have 6 to the 1. When n equals 0, I have 5 to the 0. N equals 1, I have 5 to the 0. So basically just like shuffled the numbers a little bit. But so these two are equal. They're the same thing renumbered. And renumbering the terms doesn't change their value. All right, so then what else can we do with it? So then the other thing we have is this mismatch between the exponents, where the top, the power is n minus 1, the bottom, the power is n. So how are we going to get them to match? Well, we can do a lot of different things. One thing we want to be aware of is we like the n minus 1 because the n minus 1 corresponds with our format for a geometric series. All right, so what we can do is just pull a 1/6 out of here. So this is equal to sum from n equals 1 to infinity of 1/6 times. So sometimes you have to algebraically rewrite what you are summing. The summand, can we call it that? I've never heard anybody say that. It could be the summand. Anyway, the terms, you're rewriting the terms. So if I do 6 times 6 to the n minus 1, I get 6 to the n. So I can basically just factor out a 1/6 that way. And then I can also, look at how the exponent distributes over the fraction. This is equal to 1/6 times 5/6 to the n minus 1 power. All right, so now I've gotten to the point where I can recognize that this is a geometric sequence with a sub 1 equals 6, equals 1/6, and r equals 5/6. So the series is geometric with a1 equals 1/6 and r equals 5/6. And then we note absolute value of r equals absolute value. That's a funny looking equal sign. Absolute value of 5/6. I'm cracking up because fail is over here just distracting me, which equals 5/6, which is less than 1. Therefore, the series converges. And furthermore, since we've been asked in this to state the value, give its sum, we can say what it is. So this is sum from n equals 0 to infinity. I'll just restate the problem of 5 to the n over 6 to the n plus 1 equals, and then we'll just go to our geometric summation formula. 1/6 over 1 minus 5/6, then, hey, it's 1. Ba-bing. Okay, so there you go. You're doing infinite series. We're starting with geometric series. So we have two ideas right now about series. One is that if we have a geometric series with absolute value of r less than 1, then that converges and we have a formula for it. Right? So if we have a geometric sequence and the absolute value of r is less than 1, it converges and we have a formula for it. And if absolute value of r is greater than or equal to 1, that diverges. And then the other important thing that we have, the nth term test, is that if the limit of the terms is not 0, then the series diverges. So those are two major theorems in 9.1, and we will do more fun things with series next week. Woo!